Lesson 4.4, Congruence and Transformations. Can you identify congruent figures? Can you describe congruent transformations? Can you use theorems about congruence transformations? The definition of congruent figures is, congruent figures, two geometric figures are congruent figures if and only if there is a rigid motion or a composition of rigid motions that maps one of the figures onto the other. This if and only if statement is the definition. The second sentence, congruent figures have the same size and shape, is a consequence of this definition. Again, the second sentence is not the definition. All right, let's take a look. Can we identify congruent figures in the coordinate plane, and can we explain why? Let's first take a look at the two triangles. These two triangles are congruent, so I'm going to say triangle STU is congruent to triangle HIJ because there is a, looks like it's a 180-degree rotation. And that rotation maps this figure onto this figure. Saying that the figures have the same size and shape is not good enough in the explanation. Let's take a look at these green squares. We can see that square NPQR is congruent to square ABCD because of a translation. In this particular translation, I think we can identify it. If we're going from here to here, I'm going to count over 2, so that's going to be x plus 2. And then after I count up 2, I got to count up 1, 2, 3, 4, 5, 6. So I've got 1, 2, 3, 4, 5, 6. So this will be y plus 6. So these figures are congruent because there's a translation that maps one figure onto the other. Now let's talk about these. This is triangle KLM congruent to triangle EFG because there is a reflection and a reflection over the x-axis. And if we want to write the rule, x comma y maps to x comma opposite of y. Again, the figures are congruent because we can find a rigid motion that maps one figure onto the other. Okay, stop the screencast and see if you can do this. Okay, and these are the congruent figures, and these are the reasons why they're congruent. Let's take a look at this. Describe a congruence transformation that maps. Now this is the pre-image. That's where we're starting from. And we want to see how we can get to the image. All right, now it looks to me like I can reflect over here. So it looks like I can reflect over to this other side. So I'm going to write x comma y, and I can reflect ABC to this thing right here, figure right here, and that's going to be x comma opposite of y. And then from here it looks like I can translate. So x comma y maps to, and it looks like I want to move 1, 2, 3, 4, 5, x minus 5, and I don't have to move up or down. So because I was able to do a reflection over the x-axis and a translation, these figures are congruent because I was able to go through rigid transformations that map one figure onto the other. Okay, now it's your turn. See if you can go ahead and map triangle JKL to triangle MNP. Stop the screencast and see if you can do that. Now this is my answer, and I needed to go through two transformations. I needed to go through a reflection, and then I needed to go through a translation. Okay, reflections and parallel line theorems. Let's take a look at what happens if you reflect over two parallel lines. Let's take a look at this figure right here. I have my pre-image and I've reflected. That's my first reflection. And then here's another parallel line and I have reflected again. And I want you to notice I'm going to go ahead and change here. I'm even going to change the orientation here. And you can see that even when I change these things, it looks like the original to the second reflection, it just looks like it's a translation. Like this just got scooted over here. And that's what this is saying. This is saying if you go through two reflections over parallel lines, it's as if it's a translation. Okay, let's see what we can get out of this here. Now, reflections, remember this is acting as a perpendicular bisector, so I'm going to write a congruent mark and congruent mark here. Now this is also being reflected. This is acting as the perpendicular bisector, so I'm going to put two tick marks and two tick marks. So the distance from here to here is D, and so you can see that the distance from A to A double prime is going to be 2D, because this is a length of D, and when I double this part and double this part, it's just going to double my answer. Okay, let's take a look at this problem. We're being told that HB is 9, and if this is 9, certainly this is 9 too, because this is acting as a perpendicular bisector. This length here is 4, and this length right here will be 4 as well. So altogether from here to here is going to be 26. Name any segments congruent to each segment. So we can say GH is congruent to, well, all these other segments, G prime, H prime, and G double prime, H double prime. So all of these are congruent. Now what about HB? Segment HB right here, HB is congruent to B, H prime. Now what about GA? Segment GA is right here, and it will be congruent to this other side because this is acting as a perpendicular bisector, so it's congruent to AG prime. Explain, does AC equal BD? Okay, now AC is the distance. Distance is the shortest path from one line to the other. And BD is also going to be perpendicular, and it's also representing the shortest distance. So the answer is yes. These lengths are going to be the same. What is the length from G to G double prime? And the answer is, it is 26, because 26 is 9 plus 9, 4 plus 4. So all of this length from here to here is going to travel the same amount as this. So they all travel the same amount because it's a translation. All right, let's see if we can describe a single transformation that describes a blue figure to the green figure, and that's going to be a translation. So two reflections over parallel lines makes a translation. In this particular case, because this distance here is 1.6, we know from the very beginning to the very end here, that's going to travel twice as much. So that's plus 3.2 y. Oops, I need to have a comma there. X plus 3.2 comma y. Okay, what is the relationship between P prime and K? Line K is the perpendicular bisector of P prime. That's the nature of a reflection. Okay, what's the distance between P and P double prime? Well, we know that this distance is 1.6, so this distance from here all the way here will be double, 3.2. Now let's talk about reflections over intersecting lines. And I have an example here. Okay, so here we have two intersecting lines and we reflect. Let me change this a little here. Okay, so this is a reflection, and then this is a reflection over here. Now I'm going to change it just a bit so you can kind of get a good feel. Look at how this relates to this. And I'm going to change the orientation a little bit, see if I can't turn things around. Okay, and you should get the feel that this to here is a rotation. So from the beginning to the very end is a rotation. And that's what it's saying right here. So if you rotate it over two intersecting lines, it's as if you have done a rotation, and the rotation will be a rotation of 2x degrees. Okay, let's see why. All right, here's A right here, and here's A prime, and it's been rotated. So we know that this angle and this angle will be the same. This has been reflected, I'm sorry. This has been reflected, and this is going to act as the angle bisector. Okay, now there's a reflection from here to here, and this is going to act as the angle bisector as well. So this whole angle right here is x. That's what it's saying right here. And from the beginning all the way to the end, since we're doubling and doubling, this angle will be 2x degrees. All right, let's take a look. They want us to figure out describe a single transformation that will map F to F prime. When you're reflecting over two intersecting lines, it's as if you're doing one rotation. So it's going to be a rotation from the blue fish to the green fish. It's a rotation of, and it's always this angle doubled, 140 degrees. All right, to go from the blue figure to the green figure, and again, these are two intersecting lines, so this is going to be a rotation of, and we're going to take this number and we're going to double it, so a rotation of 160 degrees. And that's the end of our